thinking about is the user friendliness of it. If you want millions of people to have these in their homes, you want to figure out a way that they can operate them without having to be chemists or even very good cooks or anything. So that's why I'm looking at electronic instruments for measuring its progress, because as much as we can automate that at a low cost, then people can easily figure out just how much CO2 they're capturing and report that, or just get the satisfaction of knowing that it's working.
Okay, hello everyone. We're here for CYAN meeting. David Wilson is going to present some of his work, and we're going to talk about it shortly thereafter.
Okay, this is an update. If you saw what I presented last week, it's a variation on the what I showed then with the aqueous CYAN in a 1 liter soda bottle. And I've got 3 new topics to update you on that are listed there, which is the agenda. So just for background, the original old CYAN looked like this. And I actually made, this was starting with DAHL's original version that had water in there to hydrate the material in a coffee filter. And I was wondering what would happen if I just dissolved the material in the water and ran it from that. Then it occurred to me that doing it in a bottle would make it more vertical, so the bubbles would travel farther and give better opportunity for actually absorbing some CO2. And the new thing I added is I built a probe to measure the electrical conductivity as we proceed with the capture, because that's been shown to be an indicator of where we are as far as grabbing the carbon dioxide. Also, before we get started, I noticed that the reaction was proceeding very slowly. And I took a look at the air stone, which is what pushes the air through and makes it into little bubbles. And it looks like it's completely crudded over with, I don't know whether that's calcium carbonate precipitate or what. So I replaced it with a new one. And you can just see that the new one looks a lot nicer than the old one. And comparing what the bottles look like when you've got the air bubbling through, the new air stone provides a lot more bubbles. And the photograph doesn't quite show how dramatic the difference is. At first, it was actually bubbling out the top.
Wow.
So let me jump ahead a little bit on this. Last week, I mentioned this paper by Mr. Hahn, in which he did a similar experiment with different amounts of calcium hydroxide in solution. And he monitored both the pH and the electrical conductivity. And he got this chart where he shows that at the point where the pH drops down to 10, in fact, when it gets there, it kind of plummets. That's the point where the electrical conductivity reaches a minimum. And I guess that's because there aren't any more ions floating around right at that point. So I thought that would be a good indicator where we should stop our run, because after that, you're not absorbing very much more CO2. And what we really want to do is to precipitate it out in the form of calcium carbonate. And that stops when pH reaches 10. So I built this probe. I actually was inspired by this project on Hackaday. He calls it a $3 electroconductivity and part per meter sensor. And mine's even simpler than his, because he measures the temperature and uses that to adjust the readings, because the conductivity is temperature sensitive. But I figure in our setup, the temperature is not going to change very much, at least not enough to matter for what we're doing. So I just built a simple probe that's basically a resistor divider. We have a source of voltage, which is just an output of one of the pins of this processor. In this case, it's a Feather M4, which could just as well be another kind of Feather or an Arduino or anything, any kind of processor like that, a known resistor, and then the probe here, which when it's out in the air is just an open circuit. I've got two pieces of wire which are clipped from a paper clip, and I put them through the holes of a button to keep them in place so they'd stay at the same distance apart. And that goes to wires that connect to this feather. So one end of the probe goes to this node here where you can measure the output voltage, and the other point goes to ground. So this V out changes as the resistance between these wires changes. So when you actually put it in solution now, the liquid will conduct electricity and it'll look like a resistor. But what you need to do is calibrate it, because the actual resistance between these two wires doesn't tell you anything unless you know what their geometry is. And so I calibrate that by putting it in solution, which I can estimate is about 8,000 microsiemens per centimeter. And I'll show something about that in a minute. But the other point is, if you just apply a constant voltage to this circuit, and there's a voltage across these wires here, and it's in a conductive solution, it'll start moving the ions around, which will disrupt the accuracy of the measurement. I don't know whether it's polarization or electrolysis or what that's happening, but I tried connecting this up to a standard ohm meter, and the results just went all over the place. They were varying and just going crazy. And that's when I came to understand that you have to just pulse the measurement very quickly so there isn't enough time for any kind of electrolysis to happen. So here's Hans' paper again. And based on his results here, where he measured the conductivity now at 7,000 microsiemens per centimeter, I set up a similar case and adjusted the parameters in the program so it would convert the voltage to the resistance rating to the actual conductivity. So the newest experiment, it was like the one from last week, but I put the conductivity probe in it, and I decided to estimate the starting conductivity was 8,000 microsiemens. And for the Americans in the audience, and the double E's, a Siemens is just a unit of conductivity, which is reciprocal of an ohm. It's also called a mho by American engineers because it's ohm spelled backwards. So I pumped air through the system like I did before, measured the conductivity every 30 seconds and plotted it. I also measured the pH just for comparison. And I have to use the this pH paper on it because I don't have a electronic pH probe, which I'm hoping to buy sometime. And the results, got two different regimes here. For the first 14 hours, it was proceeding very slowly, as I expected the conductivity to reduce, but I thought it would happen faster than that. That's when I realized that I had an old air stone and it wasn't making a lot of bubbles. When I replaced the air stone, it started moving a lot faster. The other thing that's kind of odd here, though, I'm still baffled by it a little bit, is once I started running the system, the conductivity actually went up for about an hour, up from 8,000 to say over 11,000 before it started dropping very slowly. And I don't know what that was about.
Yeah, that might be due to the CO2 actually dissolving in the water. When it dissolves, it creates, well, a carbonic acid, which is hydrogen ions as well as carbonate ions.
Okay, that's good to know. So I'll see if there's a way I need to take that into account next time. Mm-hmm. So then when I replaced the air stone, the whole thing went from pH of read the pH on this scale here, approximately 12 to approximately 6, about 10 hours. And conductivity kept on dropping until we were at the very end there. And then it flattened out, actually started going up a little bit. So that's about all I have to show there. Main point is just we need to figure out, okay, understand overshoot, and DAHL has an explanation for that. The air stone is also called a sparger, which is apparently a technical term chemical engineers use for something that bubbles a gas into a solution. Maybe there's another way to do it that doesn't need to be cleaned. It may just be part of the process that we have to either clean or dispose of the air stone after a certain number of hours of operation. And continuing ideas for automating the process. Even an electronic pH meter, which is sort of expensive, but I've also shown we can do a resistivity measurement for very cheaply. I'd like to figure out how to pump more air into it so it moves faster. And then a question I have is, how much am I influencing the results by using tap water? So I bought a jug of distilled water that I'll use next time. Also, as we discussed, the sorbent probably isn't very pure. It's just this bag of agricultural hydrated lime, which isn't guaranteed to be 99.9% pure or anything. So it's probably got some impurities. And then finally, this is still an issue. When we finish operating with this soda bottle setup, we have this precipitate sitting in the bottom, which we'd like to be able to either isolate or dispose of or even use for something practical. It's not clear what the best way is to get that out of there. Last time I tried siphoning the liquid out from the top, leaving about an inch of liquid in the bottom, and then I dried it out on filter paper, but it's obviously not the best way or the most efficient way to do it. So that's it for today.